Yeah, so here we will be starting now. I'll share the screen. You all can hear me right?
Yep.
I am audible, right?
Yes, yes, you are.
Okay. So I hope you all have gone through the slides and the blog I shared earlier. Uh, did you all? I hope you all done that. So in this session we'll be just devising some of those concepts, and then we'll be doing a code implementation of that transform model. So in this implementation, uh, we'll be converting a Portuguese sentence to English sentence. So basically, we'll be doing a translation task, which is a sequence to sequence task. So we'll be doing a code demonstration of that. So I think we'll start now. So right, this is your attention model. All of that is relevant. So at first, we just install all the dependencies. So all the dependency we need. So basically, this notebook is taken from TensorFlow documentation. So this is their official implementation of uh, transformer and then inference from that only. So yeah, at first we'll just install all the dependencies, and then it's just importing all the libraries we need. So now we'll download the dataset. Dataset is a transition official TensorFlow dataset only. So this is just you just ignore the code. I'm just telling you all to just focus on what's happening there. So you can just ignore what actually how is the code flow. You can ignore that for now. So just focus on what is happening. Uh, what's happening at the end of it. So we just need to know like how the transformer works. Uh, in actuality, you won't be using you won't be implementing it again. So it just to know like how it works in depth, right? So it's here. So you're downloading the dataset here. Then it's just printing some example of the dataset. So there is a sentence in Portuguese. Sorry. Meeting is getting recorded. No worry. Okay. So this is an example in Portuguese. So and then we'll try to convert it into English at the end of this notebook. Right. So just open the slides again. Can you all see the slides? Hmm?
Yep.
Yeah. So if you see this transformer model, basically, so you feed inputs and then convert those inputs into input embeddings, right? So you first tokenize the input and then convert it into embeddings, right? So this is how we'll do it. So now focus, right? So at first we'll set up the tokenizer. So in this notebook, the tokenizer is taken from some TensorFlow tokenizer, some model trained by TensorFlow only. So we import the tokenizer here and then we save it right now. Okay. Then this is just displaying all the methods available in tokenizer. So now we'll see how tokenizer work, right? So this is one of the example in the dataset. So this is one of that example, right? If you see, and when you improve searchability, this is that example, right? Using the tokenized method, you convert it into token IDs. So basically, you convert all this sentence into numbers. We need numbers to deal with in our machine learning models, right? So we convert this sentence into numbers, right? And then using the detokenized method, we just we can convert it into sentence again. So we use the detokenize to same this encoded part, this encoded we encoded it first, then just to check whether we can go back or not, we converted it into again into the string. So you can see like using these methods, we can convert our strings to numbers, and using detokenize, we can again convert it into string only, right? So we'll just convert all of our data set into strings, right? Into tokens, right? So this is just demonstrating all the maximum tokens per example. So in each example, these number of tokens can be there. Just ignore it. Just use this information. So now we'll prepare our dataset such that we can feed it so that we can feed it into model directly. So we'll set up a data pipeline. So this is also like simple Python stuff. Just you can just ignore it for right now. It's not related to model, right? So we are preparing our data set such that we can feed it into our model, right? That's what it's doing. It's not that important information. So now it's same thing. Now we'll come to the main part, components of our data set. So see, this is the transformer model. So at first you input embedding. So you tokenize your data set and now you have your embeddings done. So using tokenizer only you can do the embeddings, right? So now we are here, right? Now we are here. We need to implement rest of it. Is everyone here? Just
Yeah, you're
confirming.
audible.
Yeah. Okay. So right. So the embedding and positional encoding layer will implement now, right? We tokenize our inputs and now we'll implement embedding and positional encoding. So right. So this was the formula mentioned in the paper, right? So you can see the paper and also we mentioned it in the slides earlier. So this is how it's implemented. Just you can see that you can get it sine and cosine part, and this is the implementation of the same. So I won't be going much depth in like how we're doing with Python. It's just simple Python. You can just read it, and I will share the notebook at the end of the lecture, so you can just read it and go ahead, right? So won't be going like how it's done actually in Python. So hope you are all good with that. Is that fine?
Yeah.
Someone else?
I guess some
Should I go
mistake.
deep in that right now? I don't think there's a need for that. Otherwise, we will have a session of like 2 hours. I don't think anyone have that much time. Someone of you can speak. That would be great. Okay, in that case, I'll just go ahead. Thank you. Cool. So this is our encoding part. So basically, we are doing encoding here. Then think printing the shapes of and basically encoding from it. So yeah, this is the class for encoding. So we did we defined two layers. First is our embedding, and then second one is our position encoding layer. And at the end, we just sum both of these, right? Just the same in the model. So we had our embeddings and we had our position encoding. So at the end, we just sum both of them. X is our embedding, and X we defined here as embedding, and we add position encoding to it, right? So it's the same stuff. So at at the end of each layer, there is a adding and normalized part. So we just define that class. I think that's defined already. Wait, I think that's somewhere below. Okay. So now we'll come to obviously. So we first have the attention class, then we add a normalize. So right. So we'll first see attention, right? So there are three types of attention. Right? This one, and this one. See the base attention layer, the cross attention layer, and the global cell attention layer, and the casual. Oh, sorry, it's for the nodal, right? And the casual cell attention layer. So these three are the important ones. So we'll be using. So this is just basic demonstration of how uh, attention works. So in the base attention layer, it's not in the model. It's just a basic implementation of how uh, attention works. So this is taken from the inbuilt library of Keras only. So we implement the MHA layer, multi-attention layers, then we just add and normalize, right? So there's not a TensorFlow didn't provide the implementation for it, so I will demo it in some other medium. But I'll demo it again in some other medium. So not in this session, we'll have another session, or maybe in some other session we'll do it. So right, uh, so this this is the cross attention layer. This one layer we get our key and values from uh, encoder part, and then we get the query from decoder part. So this is our cross attention layer. Uh, Also, same thing. Get our query from uh, decoder part and get our key and context from key and value from our context, which is the encoder part, right? And at the end, also we just add and normalize. This is your potential layer. Similarly, your global self potential layer. This one. So it's also the same. So we get all three. We get all three in the encoder part only. So all three are just your x, right? So the end at the end also we add and normalize. Right? So this is your global self attention. So again, I'm repeating that. So in cross attention layer, you get your keys and values from encoder, which is basically providing context to your sentence, and you get a query from decoder part. So you have your query from decoder part, and you get your key and value from the context, which is the encoder part, right? So in global self attention layer, uh, you get all three in the encoder part only. So all three are inputs only from here, right? In the casual self attention layer, you see all three are from the input only. So all three are from in the decoder all three are in the decoder part, and from input only. So x axis your is this your input, and at the end you also add and normalize. So these were your three attention layers. uh, Now is the network part, so I think Aniket will take over.
Yeah. So, okay, let me present just a second. Is it visible? Wait some time.
Yeah, it is now.
Okay. Wait a minute. Okay. So our whole transformer basically consists of three basic things: the encoder, the decoder, and the other is we can also have another thing. I mean, that can be separate from these two. That is the feed forward network. So these three things are main. Okay, the encoder part, the feed forward part, and the decoder part. I mean, this whole is encoder, but we are just for time being we are basically helping ourselves by dividing them into feed forward and a smaller part of the encoder and the smaller part of decoder and a feed forward network, because the feed forward network that we will be using are pretty similar. So let's first of all see what the feed forward network is. So the feed forward network consists of two dense layers. After the first one, we'll be using a ReLU activation function as well, and after the second one, we'll be having a dropout rate of Harvish, and also adding a normalization layer after that, after the whole feed forward network. And this is how we call it at the end whenever we want to call this layer. Okay, so this is the feed forward class that we'll be having, and all these inputs, the DFF and the D model inputs, will be basically the number of units that we have for each dense layer. This will be 512, and this will also be, I guess, 512. I mean, this will of course depend on what is the output from this normalization layer that we get. So DFF will always be dependent on this, whatever we get from the other part of the encoder or the other part of the decoder, and the D model that we'll be outputting will be our choice. And basically, it is what we want to input in this while we do this encoder to decoder transportation of the value. So we will basically take it 512 as we will be understanding while going through the model from the paper or the slides as well. Yeah, that will be easy for you to gain as well. So yeah, I mean, basically what we can see that whenever we get an input from here and whenever we pass the output from decoder, both of them should be of the same size first of all, because I mean the multi-head attention layers are also similar that we are using. So yeah, the sign should be same. I mean the size should be same for that. And here we are just checking for that the input size is equals to the output size of this feed forward network, right? Okay, and after that, now we'll be seeing uh, how we'll be implementing the whole encoder. Now, to implement this whole encoder, we'll first have to implement this smaller encoder layer as well. Okay, so for that, we'll be using, as you may know by now by reading the whole paper, that encoder only uses self attention, while the decoder uses causal attention as well as the other one, I'm sorry, cross attention layer. So in the encoder, there is only self attention that is class and implemented earlier, and the number of attention heads you'll be passing that will be defined by you, the D model that we have already, and the dropout rate. These three things we'll be passing to the self attention layer. And then after that, we have the feed forward network, and this class is also defined above here. We just now defined that class. So this is how we create the encoder layer. Okay, and again, we are checking for the sizes and all. It's not a problem. And this is the whole encoder class, which consists of encoder layers. Okay, so we are using one encoder layer only right now here. And okay, so no, I'm sorry. So we'll be using multiple encoder layers, yes, and that is evident by using this formula here, in which we have passed the number of encoder layers that we'll be using, right? So it appears to be one, but there are multiple layers like that: MHA, MHA, then feed, MHA, then feed, MHA, then feed, MHA, then feed. Okay, so this is how we make a whole encoder. It consists of multiple encoder layers, right? Okay, and basically in that also you are defining things like what will be the the dimension of the inputs that we'll be giving. For example, we took it 512, the len size or the vector size for vocabs, and the number of layers means how many encoder layers are you using in that encoder. And then there is positional embedding that you have done earlier as well, which includes the vocabulary size that's so around 30,000 or 60,000 k sometimes. And okay, so now comes the encoder layer, and here, as you know that this is how you implement. This is the simple encoder layer, one encoder layer that we have here, which only includes one self attention and a feed forward network. And I will be using it. I don't know how many times. That depends on you. For here, I guess we have used it 4 or 6 times. That will be going in the in the later cells. That will be knowing the later cells. Okay, and then there's a dropout layer at the end of each encoder. Right. So this is the encoder part completed till now. Now we'll be going on to the decoder part that we have here. So each simple decoder consists of two attention layers and a feed forward network. Now this attention layer is called, sorry, this attention layer is the cross attention layer because of getting output from the backwards and also this current outputs and doing sort of a cross relationship between them. And after that, this is the causal attention layer, which is basically depends on the previous outputs or the further outputs that we have. So this is evident from this layer that we are using a simple decoder layer which consists of causal self-attention and a cross self-attention. So this is causal at the basic, then there is cross, and then there is a feed forward network. So all of the three we have implemented earlier, and we are simply putting all the values that are required for each of the layers, the dropout rates, the number of, the vocab size, the number of self-attention heads, as well as the feed forward, things that feed forward network requires, right? And this is how we call it. So first of all, the causal is called, and then cross is called, and then we basically get the. This is used basically for printing the scores later. You'll get to know that thing later. I'll tell you that. about this data part. Just ignore it for now. And this is just for creating graphs and all. I'll tell you that later. And this is the feed-forward network that we have at the end, right? So this is a single decoder layer, and we'll be using multiple, and that is how we define a decoder class, and which includes the number of layers that we'll be using as a of each decoder layer. Okay, and the same positional embeddings and other things will be defined here, and this is how we call it. So first of all, we'll be having a positional encoding of x. No, positional encoding could be this or this, whatever, and whatever. Whatever we pass it, and then we'll be having this thing. Sorry. Okay, so we'll be having a dropout layer after that. That will be somewhere here, I guess. Yes, and after that, we'll be having what do we say? The decoder layers. We'll be going at the. We will be implementing it the number of times we want. That sort of imitates the way of having multiple layers, right? We'll be getting X output from the same layer again and again and again. So maybe saving the what we know as the model size and stuff. Okay, and then whatever we get as output is our output. And here again, there's a size checking and all. Ignore that for the time being. Yeah. So now we have all things we need. We have the encoder itself, the decoder itself, and now we'll be making the whole transformer from these two classes that we got at the last, which consist of the encoder part, passing all the information to it, the decoder part, passing all the information to it, and the final layer that we have, which will be a dense layer and having the number of units would be same as the target vocab size. For example, you are having a vocabulary size of about 30,000 words. Like you will be like you want to model to only model those 30,000 words or 60,000 words, whatever you have. So yeah, you can pass it according to you. And yeah, so this is how we call it. First of all, we call the encoder. That gives us okay. First of all, we call the encoder, and then the decoder part, and then the logics. That is the final layer. That is the dense layer, final dense layer, and yeah, the dense is the output. That this is just for exceptional handling. Don't focus too much on it. Yeah. So yeah, this is pretty much it. How to make a transformer at this point. And okay. Yeah, so these are all things. Okay, yeah. So these are all things. What is the last output shape of the outputs that we get basically? And this is the transformer summary. How many parameters or other stuff? Total parameters, non-trainable parameters. There are no non-trainable parameters because we are making the model from scratch. So all the parameters will be trainable, of course, and they will be trained on. Yep. And yeah. Okay. So this is how we are preparing for optimizing it. I guess Paramveer will be taking on from this part, the
Yeah,
optimizer part.
yeah.
Yeah, sure.
Is my screen visible?
Yes, yes.
Okay. So this was all about the model only, right? So now we'll go ahead training the model. So unlike most of the machine learning models where we use a constant learning rate, we'll be using a variable learning rate and it will vary like this as explained in the paper. So basically we'll be custom scheduling our learning rate. So basically this class implements that formula only. So you see, uh, this is implementation of this formula only. It was mentioned in the paper, so we are implementing that, right? So now our landing rate will vary according to this schedule, and this is our optimizer. So Adam optimizer we are using. So it's our landing rate and all those different parameters. Now this is how our landing rate is varying. So graph of that only. Uh, and this is our loss. Now we'll calculate our loss. The loss is basically a categorical cross entropy only. So yeah, this is how we calculate our loss, and this is how we calculate our accuracy. Basically, these are functions like common machine learning functions. So now we compile our model and then fit it into dataset. So this is the accuracy and loss part. You can see it model. Okay, so runtime got disconnected. No worries. So now we'll run it into some sentences and uh, then we'll try to translate them. Right. So this is our translator class. You don't need to worry about it right now. So this is not something we'll go into. Just skip it for right now. So this is not related to transformer. So I will just skip it right now. So this is our translator. So we initialize our translator here. So and then we'll translate our sentence into translate our Portuguese into English sentences. So this is basically printing the function. So yeah, this is our prediction, and this is from the data set, ground truth from data set. So it works, right? So at last, I will just go through everything one by one again. So everything about the transform model, and again I will go through the code. So pay attention this time, right? So about the transformer, can you all see the slides? Can you all see the slides?
Yes, 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 yes. We will.
Okay. So again, transformer model. So it was introduced in the paper, and this is basically the model, right? So let's go through one by one again. So we have self-attention. So this is how self-attention is calculated. So you have three variables: query, key, and value. The query is your input, basically your input you are passing to the attention layer. And key and value are basically your context. You either have that context or you either want to generate that context. In case of cross attention layer, you get that context from encoder. But in case of other two attention layers, uh, you try to predict that context by yourself using training a model. Basically, you initialize weights and you try to predict those weights. So go ahead. So you know, like how self attention is basically uh, predicting how well a sentence is related to how well a word in a sentence is related to other words in that sentence. So how well is teacher related to book and how well is student related to book and all basically dependency between all those words, right? So this is how we calculate our scaled dot product attention, and multiple layers of scaled dot product attention makes a multi attention, right? Uh, this was the formula, and this is the same implementation of that formula only, and multiple uh, scaled dot product attentions give us the multi attentions, right? So basically concatenate all those attention weights and we get our multi layer. Right. So this was the positional encoding we use at the starting of the uh, at first at the with this is the positional encoding layer we use with our input. So we need to make sure that our model remembers the order of that sequence. So we have our sentence like this one, the teacher taught the student with the book. So uh, in RNN we go back to input again and again, right? In RNNs, if you know about that, if you don't know, just ignore. But in the motivation of self-attention is that we don't want to go back to our data again and again. So we want to minimize that, basically uh, eliminate that step and basically increase our speed and model performance. So for that we use this encoding so that we know like we can make use of a order of the sequence, right? So, so encodings are the same dimension as the embedding, so that we can sum them. So you see it here, encoding and embedding, we sum them, right? So we need to have same dimensions. That reason. Then we have the feed forward network, and there is that first ReLU function and first layer of the WX plus B. Then we apply the ReLU function. Then we apply the second weight and add the second bias. So basically, two linear transformation with a linear ReLU operation in between. So this is common between uh, all three of attention blocks. So right. So now again combining it all. So we have our inputs.
What does this do?
Sorry.
What does this feed forward network do?
So basically we output, so just I'll go back again. So in attention, you have context generated, right? In attention layer, you have context and relationship between uh, your words and sentences, right? So using this network, you basically convert that such that you can convert that context so that you can pass it, right? Basically for uh, at the end your output will be probabilities, right? So you get that. At the end, you will be outputting. You have a dictionary of tokens, and you will be outputting probabilities of each word in that dictionary, so that we know which words could be probable answer to our questions, right? So,
Yeah, I mean, the feed-forward network basically helps in predicting those probabilities, but whatever
right.
by training on the data set that we have
So
at
basically, we
hand.
convert it into like in this pitboard, this network basically give us our keys and values. Keys basically give us our key and value pair, right? So that we can pass it out. So pitboard network is basically just converting our context into the output we need, right? Basically, just understand it like that. We had our some matrices output of the multi-attention part. We need some keys and values from that, and that feed forward network does the same. So in most of the machine learning models, we use it just like that. So you have something matrices and some something like some layers, and which gives some output of some matrices and all that stuff. Then you use a network, feedforward network, just to convert it into relevant uh, probability or relevant answers we need. So here we needed like two key and value pairs. Here we need a key and value pair. So basically, we get it from feedforward layer, right? Just get it like that. Got it? You basically had your input and then you convert it into such that you basically convert it into an output, right? Got it? Hello.
Yes.
Yes, I'll just repeat it again. So you have a output from previous layer. You want to convert it into an output which is readable further in the model, right? So basically for that use your feed forward network, right? The- This is in general for any machine learning task. There may be a specific reason for in this specific paper, so you can read the paper for the same, right? In general, in any machine learning kind of task, we use feedforward network for this reason to just linearize our model. Right? So you have this network, feedforward network. So yeah, where was I? So basically, one multi-head attention layer, and basically this one part makes one layer of encoder. So in the code, we use like four layers of this, and which make our encoder part complete. So four layers of four encoder layers make our encoder. So we get the output of key and value from here. Basically, that is called context in the code. I will go in the code again. So in output part, there is first the mask multi attention, then then this one the cross multi attention, and at the end we output our probability. So I will go through the code again, starting. So first the installation, then imports, then the dataset part, downloading the dataset, then the tokenizing our input. So we get a outside tokenizer and then tokenizer input into numbers, right? So this is the tokenizer part, and then we set up our data pipeline so that our model can read our data. Right? This is the testing data set. Uh, these are various components of our model. So this is the first embedding and uh, encoding layer. So this is the encoding layer, uh, and so basically you first get embedding from the inputs, input your X, right? Get embedding from your input and then add the encoding to it, right? Basically, this is how you're calculating positional encoding earlier, and then you are adding the embedding part to it, right? Then there is the add and normalize layer. So that's add. This is how a basic attention block works. So this is just an example of that. Uh, this is how your cross attention layer works. So you see this part, right? So you have a context and your inputs, right? So context is con- you get context from the encoder part, and which is key and value. You get key and value from these two arrows. You get key and values from the uh, context for the encoder part, and you get query in the input only. This is the decoder part in this case, right? So this is how your close attention work. Uh, this is how your global self attention works. So you get all three of these from input. So all three are X only, key value and query, right? So at the end you do a add and now. This is your causal self attention layer. So in this case, also you get all three key value and query from your input only. So these are all X right here, and at the end you do add and now. So this is your feed forward network. So first two layers and activated by ReLU. So in the first layer you do a ReLU activation, and this is the final drop off layer. So at that also you do it to add and now. So this is as a whole the encoder layer. So in the one encoder layer you have a multi-head attention part and one feed forward part. So you have this is the global part, global self attention we used earlier. So and this is the feed forward part, right? So this is the sample encoder layer initialized here. Now the entire encoder will consist of multiple encoder layers, right? So we define your number of layers here. At first, so we need to consider this one only, this one also, this one as well. So we do our embedding and encoding here. So if you remember, this class did both of them. So we first got our embeddings and then added the encoding to it, right? So this is our encoder layer. So we use number. I think it's four down there. So at the end there drop out layer, right? So this is the decoder part. So one decoder layer will consist of two attention. So first one is your causal self attention. Second one is your cross attention, right? And at the end there is a feedforward network. So this is your decoder. So this is the whole transformer now. Uh, have an encoder, you have a decoder, and at the end you have a dense layer for the final output. So yeah, basically you get the encoder, you get the decoder, and you just output the final layer. This is just error checking, just ignore it. So yeah, number of layers we initialize as four, and these are all the hyperparameters. So we initialize our transformer here and just try to just uh, predict our output here. This is summary of the model and parameters used in the model. Then we use a variable learning rate. So this function demonstrate like how we define that and how we do that in the code. So this is our learning rate varies, and this is our we are setting up the losses and matrices. So that's that. Then we compile and fit our model with our data set, and these are all the accuracy and losses stuff. So translator you just ignore for right now, not related to transformer part. Uh, so then we just try to translate our uh, Portuguese to English, right? So it may all be a bit overwhelming, right? I suggest you all go through this notebook once. I will share it and try to do some parts of it by your own if you can do. If you can just see make like two windows and try to do it in one window and see from the other window, that kind of stuff, just to practice how it works, right? And there are like quite detailed instruction in this notebook as well, so I don't think you'll have any trouble understanding it, right? So if you have this, you can just post doubts on the Discord channel, right? There are some there, I will answer it after session. So yeah, does anyone have any doubts or anything else? So as assignment, I was thinking maybe I should not post that notebook and just let you finish it. Yeah, you can use PyTorch, no worries. That, that is a technology. You can use anything you want, right? No issue with that. Any other questions or anything else? Yeah, that's a good question. So basically, if you saw the slides, yeah, so this is how NLP evolved, right? So transformer is the best thing we have right now. So most of all the GPT models and everything is based on transformers only, right? You see, GPT is one of the decoder only model, right? And there are most of the all the LLMs and all the stuff is based on transformer only. So I think we need to learn that, right? I hope that's clear. And so basically, you see, we did a translation task with transformer, right? So you can see it's useful many ways, right? Any other questions? So as I was saying, like uh, I was thinking maybe I should not give you the notebook, or maybe you can just search it on Google anyways. But I will suggest you guys do some implementation by yourselves so that you can learn about like how transformer works, and or at least go through the blog thoroughly, right? So there is at least some learning at the end of it. Right. Okay, so are there any doubts?
I mean, even when you go through the notebook, you can just go through the part where the model is defined, from starting from the self attention part to the till the training part. After that and before above the self attention part, you do not need to focus on that. You just need to grab how model is made through all these classes in Python,
Yeah,
right?
basically
That is some
focus on all these transformer related classes only. Nikhil, actually
yes,
there isn't any submission now, right? Because it basically they amount the whole notebook here, and you can also find it in internet, right? So there isn't any submission right now. So I will just suggest you all to go through it, right, and just uh, learn through notebook like how the code flow works and how the transform works, right? So I will share the notebook in that case. So there isn't any submission this week. Any other question? Is that clear, Nikhil? Okay, in that case, there are no questions. We'll just end the meeting. Okay, you guys can start leaving now.
sorry.